In this video, I'll show you how to analyze the data from experiment 3, which is the determination of ethylene glycol concentration in engine coolants. So let's go ahead and look at the data in Excel. Okay, so I've gone ahead and I've put in the mass of ethylene glycol and the mass of water in each standard. I've also put in the refractive index data. Just keep in mind, this is a sample set of data. This is not the actual data that you collected in lab. The first thing I need to do is calculate the percent by mass of ethylene glycol in each of the standards. So I'm going to use this formula, equals, and I'm going to select the mass of ethylene glycol times 100, and then divide that by the sum of the mass of ethylene glycol plus the mass of water. And the first standard's concentration is 0 because there was no ethylene glycol in that one. Now I can use the same formula in all the cells to calculate their concentrations by clicking and dragging down and then hitting Control D, which fills the formula into all the cells that were highlighted. So as you can see, for the second standard, we have its mass of ethylene glycol times 100 divided by the sum of the ethylene glycol in the water. And then the next row, same formula is applied. Next, we're going to calculate the average refractive index for both of the standards. So I'll hit equals average, and then I'll select the two values that I want to average, close the parentheses, and hit enter. So that's the average of the first two refractive indices. And same as before, to apply that formula to the cells below, I'll click, drag, and highlight the cells, and then hit Control D, as in dog. It's going to fill that formula down. You can see it's calculating the average of the two values in each subsequent cell. So now we have our calibration curve data. The X data is the percent of ethylene glycol in each of the standards, and the Y data is the average refractive index for each of the standards. Now I'm ready to calculate the slope of the graph from that data. So I'll go to this cell down here and I'm just going to type equals slope. It tells me to put in the known Y's, which are these, the average refractive indices, and then the known X's, which are these, the percent by mass of ethylene glycol. So there's the slope of the linear regression. Let's get the y-intercept. I'll type equals intercept, open parentheses, same as before, known y's, comma, known x's. So it's important to have the slope and the y-intercept in your spreadsheet because we're going to use that data to then calculate the concentration of ethylene glycol for the unknown samples, the actual engine coolants that we had. But we do need to create a graph of the data for the lab report. So let me show you how to prepare that graph. I'm going to select the X data for the graph, hold down the Control key, select the Y data for the graph. Then I'll hit Insert, Scatter Plot, and there we have it, easy as pie. So next I'm going to move the graph to its own sheet, and it's going to be moved here. And next, I'm just going to do a little bit of formatting of the graph. So I'm going to add a couple of chart elements, the x-axis title and the y-axis title. I'm then going to go ahead and increase the font size of everything in the graph. And in order to do that, I actually need to select the entire chart, then go and increase the font size, and it will apply that to every part of the chart. Next, I'm going to make the data points a little bigger as well for easier viewing. Go to Format Data Series, and I'll need to click on Marker Options, and there I can increase the size of the markers. Okay, so now we have a graph that we can see somewhat. Change the x-axis title to ethylene glycol concentration, and that's percent by mass. And then change the y-axis title to refractive index, and that value has no unit. So it'll look like that. Now I'm ready to go ahead and do the linear regression. So select the data series, and you're going to right click and you're going to select add trend line. And it adds the linear regression trend line. We can see we have a really good fit. So I would like to see how good it is by displaying the R squared and the equation on the chart. And yes, that is a very good fit. So we'll call this the calibration curve. This is the calibration curve for ethylene glycol concentration by refractive index. Okay, so we have the cal curve, and that calibration curve can be copied and pasted into Word for your lab report. Let's go back to the data, and now we're ready to use the slope and the y-intercept. And you want to make sure that the slope on your chart and the slope that we calculated in the spreadsheet are the same value, and yes, they are. So now we're going to use the measured average refractive index for each of the samples. Again, these are samples that were done separately from the experiment that you did, but you'll have similar, possibly similar results. And we're going to apply the calibration curve slope and intercept to calculating these unknown concentrations. So if y equals mx plus b, and we want to calculate x, x is going to be equal to the y value, the measured refractive index, minus the y-intercept, and then divided by the slope. So we've rearranged the formula for the line to solve for an unknown x value. And there we have it. We have the concentration now of the ethylene glycol and the engine coolant for the first vehicle. One thing you're going to want to do to be able to copy and paste this formula to other cells, you're going to want to fix the slope and the y-intercept cells to cell B11 for the slope and cell B12 for the intercept. And the way we do that is we use the dollar sign in front of the column letter and the row number, and that means every time you copy and paste that formula, it will always use that exact cell for the slope and that exact cell for the y-intercept. So Control C to copy, Control V to paste, and we can see the two samples that we tested, they did have different refractive index values. One was 1.366, the other was 1.386, and they had very different ethylene glycol concentrations. Next, we're going to use that same formula to now calculate the measured percent ethylene glycol in the check or reference standard that we ran. So I'm going to copy the formula, and then I'm going to come down here and paste it. So the check standard that we ran, the first run, we got 39.85% ethylene glycol, and that standard was prepared to contain 41% ethylene glycol. So a little bit off there. I'm going to copy the formula, and I'm just going to, you can either do Control V or Control D to paste that formula down. We can calculate a percent error for each value by using this formula, equals, select the concentration to the left of this cell, and then minus the known concentration. We're going to have to use the dollar signs so that we go to the same known concentration every time. So it'd be $C, $20. Okay, so the difference between the measured and the known, and then I'm going to divide that by the known concentration, again, $C, $20. I already set the format of this cell to be in a percentage format, so I didn't have to multiply by 100. Click and drag down, and we can just hit Control D to paste that formula to fill all of the cells with that same formula. Then we can calculate the average of the percent ethylene glycol measurements in that standard that we ran in 10 replicates. We can calculate the standard deviation. And we don't really need an average standard deviation. And then finally, the percent relative standard deviation. That equals standard deviation divided by the average. And again, I've already set the cell to be in terms of percent, so it's already multiplied by 100. So we can see that we measured an average concentration of 40.2%, but the standard was known to contain 41.00%. So we're about minus 1.9% error from the known value. Another way we can compare experimental results to a known value is by using a statistical test called the t-test. So I'm going to go into another sheet where I've already set up a calculation of a t-test where you're comparing an experimental mean to a known value. That's the type of t-test we want to do here. So I've put in all of the calculated 10 replicates of the percent ethylene glycol, and they average to be 40.22. Okay, and what I've also done here is I have written the formula over on the right. So this is kind of a standard spreadsheet I use for doing t-tests. We have the standard deviation of the data set. We know how to do that. We have 10 data points. You can use the count function to get the number of data points in a series. And then we've calculated the standard error of the mean. This is equal to the standard deviation divided by the square root of the number of measurements. The degrees of freedom is equal to the number of measurements minus 1. And then we've just typed in our theoretical value. Okay, and from there we can calculate a t-statistic. So the t-value, the calculated t-statistic, is equal to the experimental mean, the value in cell C2, minus the known value, the value in C7. And I put absolute value because your t-statistic is always going to be a positive value. And then we divide that by the standard error of the mean, which is found in cell C5. And so there is my t-statistic. I can then look on the t-table to get the t-critical value. And it turns out that for 9 degrees of freedom, not 3, 9 degrees of freedom, and at a 95% confidence level, the critical t-value from the table is 2.26. So now I'm ready to compare the t-statistic to the critical t-value. And what I find is that the t-statistic is greater than t-critical. Therefore, we reject the null hypothesis and we accept the alternate hypothesis. So I'm at least 95% confident that there is a significant difference between the mean and the true value. Sadly, we would like our method to have not had a significant difference from the known value, but unfortunately it did. Another way of analyzing the data is to calculate a p-value. It's a probability value. And for this, we use the t-distribution function in Excel. So you do equals t-dist, and then what you're going to be selecting, I'll do this again, t-dist, it will tell you what to put in. So first of all, you want to put in the x value, which is the t statistic that you have already calculated. Then you want to put in the degrees of freedom, and we've already calculated that above. And then finally, it wants to know the tails, and we're doing a two-tailed. We're not looking to see if one value is greater than or less than the other. We're just looking to see if there is a difference between them. So that's how you do the t-distribution, and it's giving me a very, very small number. If the p-value is less than 0.05, then we have a less than 5% chance that the values are the same and that the differences are purely random. So we have a very small percent chance that the differences are the same, or that the values are the same and the differences are just due to random error. And because of that small probability, we know that there is a very strong likelihood that there's a significant difference between the average that we calculated for our measurements and the known value. It's kind of interesting because our average was 40.22, the known value was 41.00. When you look at those two numbers, they don't seem to be all that different, but the statistics say that there is a significant difference between them. So now that we've done our t-test and we've calculated the concentration of ethylene glycol in the engine coolant samples, and that's right here. So one was 35.18% ethylene glycol, the other was 56.38. So somewhat of a significant difference between these two samples that were taken from our vehicles. Now we'd like to see how do these values relate to the freezing point of this fluid. The whole point of engine coolant is to be able to lower the freezing point so that on a cold day when it's freezing outside, the actual fluid inside our engine doesn't freeze, it remains a liquid. So for that, we're going to have to look up some standard data. And I've gone to www.engineeringtoolbox.com for the standard data. And there they have, at different percents of ethylene glycol in water, the actual freezing point in degrees Celsius. So if you have pure water, we know the freezing point is 0 degrees Celsius. If you have 100% ethylene glycol, the freezing point is just negative 12.9. And theoretically, we could have a day outside that is that cold. And so pure ethylene glycol would also freeze, would not remain a liquid. That could damage our engine. But what happens is when you mix water with ethylene glycol, the mixtures have lower and lower freezing points, and the minimum is somewhere around a 60-40 mixture of ethylene glycol water. Its freezing point is negative 52.8, very low freezing point. At that temperature, probably not going to experience that low of a temperature in any normal location on Earth. Maybe in Antarctica you might get that low, but not in the continental US. So what we want to do is let's go ahead and graph that data. So I'm going to select these two columns. I'm going to insert, and this time we're going to insert a scatter plot that has smooth lines. So what this now gives us is the ability to sort of see how the freezing point will change as the percent ethylene glycol changes. It's not a linear relationship, it's sort of a U-shaped curve. And from this graph, we can estimate what the freezing point will be for the samples that we have run. So I've transcribed the data here, and I've already looked at this graph, so I don't want to spoil it for you, but let me show you how I came about those numbers. The first sample had an ethylene glycol concentration of 35.18. So 35.18% is somewhere between 30 and 40%. We're expecting the freezing point to be between negative 13 and negative 23.5. So we're in this part of the curve here. So I'm going to say that engine coolant is going to freeze at approximately negative 19 degrees Celsius. The next one is 56.4% ethylene glycol. This is in the lowest part of the curve. So it's somewhere between negative 37 and negative 53, maybe a little more than halfway between those. So that's where we estimated that the freezing point is going to be approximately negative 46 degrees Celsius. And that's just an approximation from the graph. So that's how we can analyze the data that we acquired in this experiment. As always, if you have any questions, feel free to reach out.